Abstract syntax notation 1 is a standard notation that describes rules and structures for representing, encoding, transmitting, and decoding data in telecommunications and computer networking. The formal rules enable representation of objects that are independent of machine-specific encoding techniques. Formal notation makes it possible to automate the task of validating whether a specific instance of data representation abides by the specifications. In other words, software tools can be used for the validation. ASN 1 is a joint standard of the International Organization for Standardization, International Electrotechnical Commission, and International Telecommunication Union Telecommunication Standardization Sector ITUT, originally defined in 1984 as part of CCITTX 409-1984. ASN 1 moved to its own standard X208 in 1988 due to wide applicability. The substantially revised 1995 version is covered by the X680 series. The latest revision of the X680 series of recommendations is the 5.0 edition, published in 2015. ASN 1 in transfer. A source of observation may generate data that is needed at another location for processing. For example, a radio telescope in outer space might produce voluminous signal data that cannot be processed locally. The recording and processing systems may be very different in nature, and may even be produced by different vendors. A consistent mechanism is needed to record, transmit, and receive data across diverse systems. ASN 1 defines the abstract syntax of information but does not restrict the way the information is encoded. Various ASN 1 encoding rules provide the transfer syntax of the data values whose abstract syntax is described in ASN 1. The standard ASN 1 encoding rules include basic encoding rules, canonical encoding rules, distinguished encoding rules, XML encoding rules, canonical XML encoding rules, extended XML encoding rules, packed encoding rules, generic string encoding rules. ASN 1 together with specific ASN 1 encoding rules facilitates the exchange of structured data, particularly between application programs separated by networks, by describing data structures in a way that is independent of machine architecture and implementation language. Application layer protocols such as X400 electronic mail, X500 and lightweight directory access protocol directory services, H323 Kerberos BACnet and simple network management protocol use ASN 1 to describe the protocol data units they exchange. The access and non-access strata of the universal mobile telecommunications system also use ASN 1 extensively. There are many other application domains of ASN 1. A particularly useful application of ASN 1, Fast Info Set, an international standard introduced in 2005, specifies a binary serialization encoding format for the XML information set that is more efficient than the text-based XML format. Example: data structures of foo protocol defined using the ASN 1 notation. Foo protocol definitions equals begin foo question equals sequence tracking number integer question IA5 string foo answer equals sequence question number integer answer boolean end. This could be a specification published by creators of foo protocol. Conversation flows, transaction interchanges, and states are not defined in ESN1, but are left to other notations and textual description of the protocol. Assuming a message that complies with the foo protocol and that will be sent to the receiving party, this particular message is my question foo question equals tracking number 5 question. Anybody there? ASN1 supports constraints on values and sizes, and extensibility. The above specification can be changed to foo protocol definitions equals begin foo question equals sequence tracking number integer question IA5 string foo answer equals sequence question number integer answer boolean foo history equals sequence question sequence of foo question answer sequence of foo answer an array sequence of integer. And the changes above that tracking numbers are now constrained to values 0 to 199. Question numbers 10 to 20. The size of the questions array can be between 0 and 10 elements, with the answers array between 1 and 10 elements. The an array field is a fixed length 100-element array of integers that must be in the range 0 to 1000. The extensibility marker means that the foo history message specification may have additional fields in a future versions of the specification. Systems compliant with one version should be able to receive and transmit transactions from a later version, though able to process only the fields specified in the earlier version. Good ASN1 compilers will generate source code that will automatically check that transactions fall within these constraints. Transactions that violate the constraints will not be accepted from or presented to the application. Constraint management in this layer significantly simplifies protocol specification because the applications will be protected from constraint violations, removing risk and cost from the development. Many other serialization technologies lack this feature. To send the my question message through the network, the message is encoded as a string of bits. ASN1 defines various algorithms to accomplish that task, called encoding rules, of which a number are defined. Among the simplest is distinguished encoding rules. The foo protocol specification should explicitly name one set of encoding rules to use, so that users of the foo protocol know which one they should use and expect. Example encoded in .The. Below is the data structure shown above encoded in .The format 30, type tag indicating sequence 13, length in octets of value that follows, 02, type tag indicating integer 01, length in octets of value that follows 05, value 16, type tag indicating IA5 string, 0e, length in octets of value that follows 41 6e 79 62 6f6 4 7 9 20 74 68 65 72 653f value. The result is the string of 21 octets 301302010516 41 6e 79 62 6f6 4 7 9 20 74 68 65 72 653f. The scope of ASN1 and .The ends here. It is possible to transmit the encoded message to the recipient by any means or any other protocol. The party should be able to decode the octets from the .The. Example encoded in XCR. Alternatively, it is possible to encode the same ASN1 data structure with XML encoding rules to achieve greater human readability over the wire. It would then appear as the following: 108 octets, and LT, foo question and GT, and LT, tracking number and GT, 5 and LT, tracking number and GT, and LT, question and GT. Anybody there? and LT, question and GT, and LT, foo, question and GT, example encoded in per. Alternatively, if packed encoding rules are employed, the following 122 bits will be produced: 01, 050 E83 BBC E2 DF9 3CA0 E9 A3 2F2 CAFC0. In this format, type tags for the required elements are not encoded, so it cannot be parsed without knowing the expected schemas used to encode. Additionally, the bytes for the value of the IA5 string are packed using 7-bit units instead of 8-bit units, because the encoder knows that encoding an IA5 string byte value requires only 7 bits. However, the length bytes are still encoded here, even for the first integer tag 01. Note also that the last 6 bits in the encoded per are padded with null bits in the 6 least significant bits of the last byte C0. These extra bits may not be transmitted or used for encoding something else if this sequence is inserted as a part of a longer unaligned per sequence. This means that unaligned per data is essentially an ordered stream of bits, and not an ordered stream of bytes like with aligned per, and that it will be a bit more complex to decode by software on usual processes because it will require additional contextual bit shifting and masking and not direct byte addressing. However, modern processes and signal processes include hardware support for fast internal decoding of bit streams with automatic handing of computing units that are crossing the boundaries of addressable storage units. If alignment on octet boundaries was required, an aligned per encoder would produce 01, 050 E41 6E79 62 6F6 479 20 74 68 65 72 653F. ASN 1 versus other data structure definition schemes. Since it is commonly used for defining messages for communication protocols, ASN 1, with its associated encoding rules, results in a binary encoding. Other communication protocols, such as Internet protocols HTTP and SMTP, define messages using text tags and values, sometimes based on the augmented backcos and a UARFM notation. The definition also defines the encoding, which is in text. There has been much debate over the two approaches, and both have their merits. The ASN 1 approach is believed to be more efficient, and with packed encoding rules, certainly provides a more compact encoding. The textual approach is claimed to be easier to implement and easier to debug with only a text editor. In the case of the Megaco protocol, consensus between the two points of view was not reached, and so two encodings, one based on ASN 1 and one on ABNF, were defined. The ASN 1 XML encoding rules attempts to bridge the gap by providing a textual encoding of data structures defined using ASN 1 notation. Generic string encoding rules were also defined for the sole purpose of presenting and inputting data to, from a user. Encoding control notation. The encoding control notation is a notation to specify specific encodings of ASN 1 types. ECN is useful to describe legacy protocols in ASN 1. It is possible to specify only the encoding of some types and then complete with the standard encoding rules. ASN 1 Information Object Class. Information object classes is a concept used in ASN 1 to address specification needs similar to the ones addressed by CORBA IDL specifications. Using ASN 1 in practice, one may use an ASN compiler which takes as input an ASN 1 specification and generates computer code for an equivalent representation of the data structures. This computer code, together with supplied runtime libraries, can then convert encoded data structures to and from the computer language representation. Alternatively, one can manually write encoding and decoding routines. Standards describing the ASN1 notation ITUT-REC by .680 ISO IEC 8824-1 ITUT-REC by .681 ISO IEC 8824-2 ITUT-REC by .682 ISO IEC 8824-3 ITUT-REC by .683 ISO IEC 8824-4. Standards describing the ASN1 encoding rules ITUT-REC by .690 ISO IEC 8825-1 ITUT-REC by .691 ISO IEC 8825-2 ITUT-REC by .692 ISO IEC 8825-3 ITUT-REC by .693 ISO IEC 8825-4 ITUT-REC by .694 ISO IEC 8825-5 ITUT-REC by .695 ISO IEC 8825-6 ITUT-REC by .696 ISO IEC 8825-7 RFC 3641 and RFC 4792. Comparison of ASN1 tools. This table provides basic comparisons for ASN1 tools, including the licenses, the runtime they support, the possibility to compile ASN1 descriptions into runtime-compatible code, and the support for transfer encodings.